here in section 13.3, we're going to use what we know about polar representations of points to help us do calculations with our old friends, the complex numbers. So let's just take a couple minutes and review the basics of this from college algebra. The complex numbers come from trying to solve the equation x squared equals -1. Because no real number will do this job. Because if you have a negative real number and square it, you get a positive number. 0 squared is 0, and a positive number squared gives you a positive. So what we do is we define I to be the imaginary unit to be the square root of -1, so that I squared equals -1. And therefore we can solve the equation x squared equals -1 to be x to be plus or minus the square root of -1, or plus or minus I. So the letter I represents this number. A complex number is a number z of the form a plus bi. So we typically use the letter z for a generic complex number, where the a and the b here are real numbers. So for example, -2 plus 3i is a complex number. A number like 6i would be considered a complex number. It's actually more specifically called a purely imaginary number. I could write this as 0 plus 6i. That there's no real number being added to it. It's pure imaginary. And real numbers themselves, like 4, are considered complex numbers. That's a real number. I can think of this as 4 plus 0i's. So the complex numbers contains the real numbers. And in college algebra, we didn't want to do anything with them geometrically because we were waiting for trigonometry here to help us with that. So what we can do to geometrically display or plot the complex numbers is to look at the so-called Argand plane. So the Argand plane, the x-axis here is the real number line. The y-axis is an imaginary number line. So for example, if I look at the complex number, or -4 plus 2i, I'm going to identify the real part there, -4, as the x-coordinate, and the imaginary part there, 2, to be the y-coordinate. So identify -4 plus 2i with a point in the plane, -4, 2. The number 0, I can think of as 0 plus 0i, so that corresponds to the origin. If I have a real number like 3, then I can think of that as 3 plus 0i. That's going to get identified on the real axis as 3, 0. And if I have a purely imaginary number, z equals -3i, I can think of that as 0 plus -3i. It's going to give me a point on the imaginary axis. So in general, z equals a plus bi is going to correspond to a point in the plane a comma b. And this is sometimes called the rectangular form of the complex number. So these are the real numbers and that's the imaginary numbers. Now we know from section 13.1 that I could come up with a polar representation of this point. So this corresponds to a polar representation r and theta. Not only that, it corresponds to infinitely many polar representations. So what we're going to do is we're going to fix r to be bigger than 0. So this actually represents the distance here from the origin out to the point. And we're going to fix theta to be between -pi and pi, excluding -pi, including pi. So when we look at our angle theta, in standard position, the angles we're going to pick from are going to range from -pi over to and including pi. So instead of picking the range from 0 to 2 pi, which is what we typically do, we're going to go from -pi to pi. And there's reasons for this. If you go on and do any kind of analysis with the complex numbers, you'll see why this is sort of a preferred interval to work on. So all of these things are going to be given names now. Okay, all of these things are being given names. So the real part of the complex number is going to be the number a. So that's the real part is there. That's going to be the x-coordinate of the rectangular representation in the Argand plane. The imaginary part of z, that's going to be b. That corresponds to the y-coordinate here. The value of r is going to be called the modulus of z, and it's going to be represented by the absolute value symbol. And this is actually consistent with absolute value. If you remember when we looked at the absolute value, say, of 3, or the absolute value of -3, there was a way to think about them in terms of distance. It was the distance from the origin. The distance from 0 is what absolute value meant. Well, if we're picking r to be positive, that's exactly what r is telling us. It's the distance from the origin. So this still, this is consistent with absolute value notation from before. The angle theta is called the principal argument, denoted by capital ARG. The lowercase ARG, the lowercase argument, is just going to be this angle plus all the coterminal angles. So lowercase argument is the set of all possible angles theta. Uppercase argument is just the one that lives between -pi and pi. All right. So let's do some examples writing off all these little bits and pieces. So plot the following points in the complex plane. Find the real imaginary parts, the modulus, the argument, and the principal argument. Okay. All right, so first thing is we have square root of 3 minus I. That's the square root of 3 plus -1i. That's going to correspond to the point square root of 3, -1. So square root of 3, -1. There it is. That's your real axis. That's your imaginary axis. So there it is. There it is on the Argand plane. Square root 3 minus I. What's the real part of this? The real part of this is the real number here, square root 3. What's the imaginary part of this? The coefficient of I, -1. What's the modulus? Well, that's r from polar coordinates. The positive r, which I know from polar, is the square root of x squared plus y squared. So it's the real part squared plus the imaginary squared. So if I go through the calculation here, root 3 squared is 3. -1 squared is 1. Add those together. Square root of 4 is 2. So the modulus is the r value. It's literally the distance from this, the distance to the origin, right? The distance of this point to the origin. All right, now to get the argument, we need to figure out the angle involved. So the tangent of theta, as usual, is the y over the x. So it's the imaginary part over the real part. -1 over square root 3. I know that reference angle, all right, because that'd be a pi over 6 reference angle, root 3 over 3. So I need to pick the angle here for the argument, the principal argument of z. I need to pick the angle between -pi and pi. In quadrant 4 with the reference angle of pi over 6. And so that would be -pi over 6. And then the set of angles, which is the argument of z, would be -pi over 6 plus 2 pi k, k to be 0, plus or minus 1, plus or minus 2, etc. So that's all the pieces parts for the complex number root 3 minus I. All right, number 2. Z equals negative 2 plus 4i. That's going to correspond to the point negative 2, 4. So that's going to give me something over here in the second quadrant. So there's my real axis, imaginary axis. I go left 2, up 4. There it is. Real part, real number there, negative 2. Imaginary part, coefficient of I, positive 4. The modulus of z, once again, that's the same as the radius of the circle that point would be on. That's the square root of x squared plus y squared, which is the square root of the real part squared plus the imaginary part squared. So I get 4 plus 16. That gets me the square root of 20. 20 is 4 times 5, so this would simplify to 2 square roots of 5. To find the principal argument of z, I need to figure out theta. The tangent of theta would be the y over the x, the imaginary over the real. 4 over negative 2, which is negative 2. I don't know an angle whose tangent is negative 2, so I'm going to have to use the arc functions for this. All right. Okay, so if I took the arc tangent of negative 2, I could pull the negative out. That would be negative arc tangent of 2. Let's see here. So that's where I want. So the negative arc tangent of 2 would be this angle down here. All right, so I need the one that's in quadrant 2, so I would need to add pi to that to get that over to quadrant 2. So theta would be pi minus the arc tangent of 2. And that would give me my argument, because that would be an angle between minus pi and pi. So that's my principal argument. Pi minus the arc tangent of 2. And that means that the argument would be this plus or minus multiples of 2 pi. So all the angles coterminal to this, pi minus arctangent of 2 plus 2 pi k, where k is any integer. Okay. So once again, we just read off the point, read off the real number, coefficient of I, and then we find the r and the theta like we would for a particular polar representation. That's your modulus, that's your argument, and then the principal argument, and then the lowercase argument, you just look at all the angles coterminal to the principal argument. We got a couple of extreme ones here. Z equals 3i. So that's going to correspond to the point 0, 3, right? Because think of this as 0 plus 3i. That's just going to land me 3 units up on the imaginary axis. The real part of z is 0 because it's pure imaginary. The imaginary part of z is 3. The modulus of z, that's the r value. Well, we could go through the arithmetic here, but you can tell that it's going to be 3 units away from the origin. So z is going to be 3. What's the principal argument of z? Well, there it is. I'm up there on the positive imaginary axis, so that's a rotation of pi over 2. So the argument of z would be any angle coterminal with pi over 2. So there's all the bits and pieces for that complex number. And finally, z equals negative 11/7. That's going to be back here. So negative z here is a real number. So there's no imaginary part at all. Negative 11/7 plus 0i. So it's going to be right there. The real part of z is negative 11/7. The imaginary part of z is 0. Just like the previous example, we can get the modulus of z. How far are we from 0? The answer is 11/7. And once again, that reduces down to the absolute value of z, right? So the modulus of z is the generalization of absolute value. It's the distance from the complex number to the origin. So we can see that actually happening here. What's the principal argument? Well, the principal argument is going to be pi. And then what's the argument? All angles coterminal with pi. Pi plus 2 pi k. K is 0 plus or minus 1, etc. Now, if you'd like, you can factor the pi out of this, and this would be 2k plus 1. In other words, it's any odd multiple of pi. All right, so what can we do with this? All right, well, first off, here's some properties. Properties of the modulus. So the modulus is the distance from z to 0 in the complex plane. All right, we've already shown that. The modulus is always 0 or bigger, and it's equal to 0 if and only if z is 0. We know that from polar coordinates. Right? If the r is 0, that means you're at the origin. Otherwise, you're some distance away from the origin. And once again, this comes from Pythagorean theorem distance formula. The product rule, power rule, and quotient rule, these aren't obvious at the moment. We'll be able to show these more easily once we get the polar form more involved here. Same thing with the properties of the argument. All right, you can actually go through and work these out. Okay, so I'm not going to dwell on these. Okay, so what we want to do is now further solidify the connection between this polar form and the rectangular form. All right, so going back to polar coordinates. All right, so we've got a point AB in rectangular coordinates and a point r theta. So we know that the x-coordinate is r cosine theta, and the y-coordinate is r sine theta. So if I put those in for z here, I get z equals r cosine theta plus r sine theta times I. I can factor the r out, and I get this sum, which is abbreviated cis. So cis theta is cosine theta plus I sine theta. And if I remember r is the modulus, I get this. I get z equals the modulus of z times cis theta, where theta is any angle in the argument of z. And this is how we're going to describe the polar form of a complex number. All right, it's your radius, how far out you go, times this cis theta, which tells you the rotation. Now, there's another way to write cis theta in terms of exponentials. You may or may not see that. Sometimes it shows up on the calculator. Sometimes cis theta is written as e to the I theta, which you could take that as a definition of what we mean by e to the I theta. But if you persevere through calculus, when you get into topics in calculus, you'll be able to really understand a little bit better why this definition is consistent with all the other things we do with these functions. But for now, in this course, we're just going to use the cis theta notation. Okay, here in example 2, we're asked to find the rectangular form of the complex numbers, find real part of z and imaginary part of c. So rectangular form, remember, that's the standard a plus bi that we used back in college algebra. The key to this is just expanding the cis notation, okay? So 4 cis 2 pi over 3 means 4 times the quantity cosine 2 pi over 3 plus I sine 2 pi over 3. That's 4 times the cosine of 2 pi over 3, that's negative a half. The sine of 2 pi over 3 is root 3 over 2. Now I'll just distribute this through here, and I get negative 2 plus 2i square root of 3. So the real part of z would be the real number there, negative 2. The imaginary part of z is the coefficient of I, which would be 2 square roots 3. Now we can get a sense of if this makes sense or not, because when I think back to polar form, if I think of that 4 as being the r and the 2 pi over 3 as the theta, I would start at the origin, go out 4 units, and then rotate 2 pi over 3, and that would get me here somewhere in quadrant 2. And so I can at least judge that I'm in the right quadrant because the real part is negative, but the imaginary part is positive. So that's kind of a quick check for us. Let's take a look at 2 cis negative 3 pi over 4. 2 times the quantity cosine negative 3 pi over 4 plus I times sine of negative 3 pi over 4. 2 times, we can use the even-odd property of cosine. Cosine absorbs the negative. So the cosine of negative 3 pi over 4 is the same as the cosine of 3 pi over 4. And that's negative square root 2 over 2. For the sine has odd symmetry, so I can factor the negative out front, minus I times the sine of 3 pi over 4, square root 2 over 2. Distribute the 2 through to each term. I get negative square root 2 minus I square roots 2. So this gives the real part of z is minus square root 2, which is also the imaginary part of z. Once again, let's see if this tracks. If I look at polar form, r would be 2. I'm going out 2 units, and I'm rotating now clockwise 3 pi's over 4. That's going to land me right here in quadrant 3, where sure enough, the real and imaginary parts, both x and y's, are negative. Now for part C, 3 cis 0, well, you're welcome to write this out. 3 times cosine of 0 plus I times the sine of 0. But in this particular case, this is a quadrantal angle. And so if I think about what's happening here, the r is 3 and the theta is 0. That means I'm starting at the origin and just moving out 3 units. So that's going to be 3 units along the real number axis. That'll get me to the point 3 comma 0, which corresponds to the real number 3. So the real part of z is 3, and the imaginary part of z is 0. Right? Now once again, if you went through the process, you could see this happening. This is just really one step away. Cosine of 0 is 1. Sine of 0 is 0. 3 times 1 is 3. Okay. But you want to start thinking of these r cis thetas, right? Taking them back to the polar coordinates. Same thing down here with part D. Cis pi over 2, there's no coefficient explicitly written, so we can think of that as a 1. So if I think about polar coordinates, I'd be going out 1 unit and then rotating pi over 2. That's going to land me 1 unit up on the imaginary axis, so that should just give me I. If you like, you can go ahead and write this out. Cosine pi over 2 plus I sine pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Sure enough, you get I. What's the real part of I? Nothing, because it's imaginary, pure imaginary. What's the imaginary part of I? 1. Okay. Now, for this next example, it says find a polar form of the following complex numbers. These are the same numbers we had back in the first example. So let me go back to the first example here. Whoops, maybe not like that. Let's go back. Let's go back. Go back. All right. So I'll just redo these. So for root 3 minus I had the modulus, the r was 2, and the argument was negative pi over 6. So I can pick 2 negative pi over 6. So this would be 2 cis negative pi over 6. And for this angle, I could pick any angle in the argument. I'm just picking the principal argument because that's the one we found. All right. Likewise, I can go back to this one. We found the modulus was 2 root 5, and the argument was pi minus arctangent 2. So this would be 2 root 5 cis pi minus arctangent 2. Z equals 3I. Well, this is a quadrantal angle again. I could look at my work I did before. I know how far above the axis it is, 3, and I know I'm rotating pi over 2. So this would be 3 cis pi over 2. Z equals negative 11/7. Once again, I can go back and look at my work for that. But I know 11/7 is over here on the real axis. It's 11/7 units away from the origin. And I can pick the angle there as pi. So this would be 11/7 cis pi. Now the way you can check all of these is actually start with your polar form and expand out the cosine plus I sine. So if you go back and expand the cosine plus I sine and then simplify things, you should get back to these formulations for z. All right, so here's where a lot of the advantage to working in polar form comes into play. And as I mentioned, there's properties of the modulus and argument that we kind of skipped over that will be very apparent when we start working these sorts of problems. So suppose you've got z and w and their complex numbers, and you've got their polar forms. All right, so modulus cis theta. Okay, so here, modulus of z, cis alpha, modulus of w, cis theta. Then if you want to multiply the complex numbers together, you multiply the arguments, so you multiply the radii, and you add the angles. So you're magnifying things by multiplying the radii together, and then you're rotating. You're adding beta to alpha. All right, we'll talk more about that later. De Moivre's theorem is the power rule. So if you multiply something by itself n times, you're going to be multiplying the modulus together n times, so you get the modulus to the nth power. And then you're adding the angle to itself n times, so you get n theta. So when you take the power of a complex number, you take the power of the modulus and you multiply the angle by n. Now the quotient rule, remember division is sort of the opposite of multiplication. So for the quotient rule, we're going to divide the moduli. Instead of adding the angles, we're going to subtract alpha minus beta. Okay? And of course, we can divide by any two numbers as long as they're not 0. So you can get the power rule and the quotient rule really the same way as you get the product rule. The power rule, once again, is just iterating the product rule n times. So let's actually go about and prove this. So let's prove the product rule. So z times w would be the magnitude of z cis alpha times the magnitude of w cis beta. So we can go ahead and multiply the moduli together. I might have said magnitude. I'm thinking vectors. It's sort of the same thing. So we're going to multiply the moduli together. So really the work here is figuring out what happens when you multiply out cis alpha times cis beta. So let's work that out. So when in doubt, write it out. Cis alpha is cosine alpha plus I sine alpha, and times cis beta, cosine beta plus I sine beta. Let's see what we get. We get cosine alpha times cosine beta. And then we get I times, let's see here, cosine alpha, cosine beta. Then we get I times cosine alpha sine beta. And then we get I times sine alpha cosine beta. And then we get I squared sine alpha sine beta. All right. Now we're just going to clean this up a little bit. We've got I squared, remember, we can simplify that to -1. That's the definition of I. So ZW equals, let's see, well, I'm sorry, this was just the cis part. Cis alpha, cis beta equals, so I've got cosine alpha, cosine beta, minus sine alpha, sine beta. So I got cosine alpha, cosine beta, minus sine alpha, sine beta. And these last two terms have I in there. I'll factor it out. Plus I times, and look what I get. I'll write this one first. I've got the sine alpha cosine beta and cosine alpha sine beta. Hopefully these ring a bell. This is none other than the cosine of alpha plus beta. This is none other than the sine of alpha plus beta. So cosine of alpha plus beta plus I sine alpha plus beta, that's literally the definition of cis alpha plus beta. And so that completes the proof. If you want to multiply z and w, you multiply the moduli and you add the arguments. Okay? It's a two-step process, right? Two-step process. Okay, and the power rule and the quotient rule follow directly then from that. All right, let's take a look at example 3. We're given a couple of complex numbers. Find the following by converting z and w to polar forms. Write your final answer in rectangular form. So what we're going to do is we're going to go from rectangular form into polar form, and we'll do the calculations here, and then we'll go back to rectangular form. All right. So changing form has its advantages. So first thing we got to do is get polar form of them. So z is 2 radical 3 plus 2i. So I need to get the polar form of it. So first off, we want to plot it. So it's going to be here in quadrant 1. Let's find the modulus of z. That's the r from polar coordinates. So we take the real part squared, the imaginary part squared. 4 times 3 is 12. 12 plus 4 is 16. 4. So once again, this would be the r value associated with this. This tells us the distance from the origin out is 4 units. Now I got to go figure out the argument. So if I look at the tangent of theta, that's going to be the y over the x. I guess I should label this, right? The y over the x, that would be 2 over 2 root 3, which is 1 over root 3. So I get root 3 over 3, which is pi over 6. So the argument is pi over 6. So one version of the polar form here would be 4 cis pi over 6. And once again, you can always check. Expand out cosine plus I sine. Cosine of pi over 6 plus I sine pi over 6. Multiplied by 4. You should get back to the original z. So here's our polar form of z. And now we'll do the same thing for w. W is negative 1 plus I square root of 3. So w is negative 1 plus I square roots of 3. Once again, let's locate w in the complex plane. It's going to be up here. That tells us our theta is going to be in quadrant 2. Step 1, we find the modulus of w. It's going to be the distance from w to the origin. I take the real part squared, the imaginary part squared, add them up, take the square root. This is going to be 1 plus 3, so I get the square root of 4, which is 2. To get the argument, the tangent of theta is the y over the x. So let's see, this would be 1 comma root 3. So here we get root 3 over negative 1, which is negative root 3. I know the reference angle here is pi over 3, but we need it there in quadrant 2. So I can take the argument of z to be 2 pi's over 3. And so I get the polar form of w is 2 cis 2 pi's over 3. And once again, the best way to check your answer is to write that out. Cosine of 2 pi over 3 plus I sine of 2 pi over 3, multiply through by 2. So now I'm going to record these polar forms here. And just double check I copied them right. So 4 cis pi over 6, 2 cis 2 pi's over 3. All right, now we're all set. What kind of calculations do they want? Z times W. So Z times W. You multiply the moduli, 4 times 2, and you add the arguments. Pi over 6 plus 2 pi over 3. So I'm going to get 8 cis, and let's see, we'd have pi over 6 plus 4 pi's over 6. That gives me 5 pi's over 6. 8 cosine 5 pi over 6 plus 8I sine 5 pi over 6. The cosine of 5 pi over 6 is negative square root 3 over 2 times 8, so negative 4 square root 3, plus the sine of 5 pi over 6 is a half, times 8 is 4, plus 4i. Now you can check this by actually going in and multiplying z and w together. Okay. What's the next thing they want? W to the 5th power. Okay. So that's 2 cis 2 pi over 3 to the 5th. So we can think of multiplying w by itself 5 times. Every time you multiply w by itself, you're multiplying the moduli is 2 each time. So it'd be 2 times itself 5 times. You'd be adding the angle to itself 5 times. So this is De Moivre's theorem. So I'd have 32 cis 10 pi over 3, which would be 32 times the cosine of 10 pi over 3 plus 32I sine 10 pi over 3. Now 10 pi over 3 is more than 2 pi. So let's think about going back to the unit circle. Where is 10 pi over 3? All the way around would be 2 pi, which is 6 pi over 3. So I need an additional 4 pi over 3. So I'd have to keep going. And that would land me here in quadrant 3. So that means that the cosine of 10 pi over 3 would be minus a half. The sine of 10 pi over 3 would be minus root 3 over 2. So w to the 5th in rectangular form is negative 16 minus 16I square root 3. Now imagine the savings here, the computational savings of using polar form. In this one, yeah, the z and the w, you can multiply these together and FOIL them out. But w to the 5th without polar form, you'd be stuck with doing this. The best tool you have right now to do something like that would be like a Pascal's triangle expansion from the binomial theorem. That still would take you a lot of time. The polar form wasn't that bad to get. And then De Moivre's theorem, it's a two-step problem at that point. And then, of course, z minus w. Oops, I lost track here. Okay, z divided by w. So that's, excuse me there, 4 cis pi over 6 divided by 2 cis 2 pi over 3. Now we're dividing, that's the opposite of multiplying. So instead of multiplying the moduli, we're dividing the moduli. 4 divided by 2 is 2. Instead of adding the second angle to the first angle, we're going to subtract the second angle from the first angle. So now I need a pi over 6 minus 2 pi over 3. So once again, this is 4 pi over 6. So pi over 6 minus 4 pi over 6 would be minus 3 pi over 6, aka minus pi over 2. So 2 cosine minus pi over 2 plus 2I sine minus pi over 2. Cosine absorbs the negative. It's an even property. Cosine of 0 is 0, so that's completely gone. So that's going to zero out. The negative on the sine can come out front. Sine of pi over 2 is 1. So z divided by w ends up being 2i. Which, once again, you could get this by taking z over w and then rationalizing the denominator, which is something you may or may not remember how to do with complex numbers, and you'd arrive at that answer as well. Okay? So, taking the time to convert it to polar in the end, it seems like a more complicated process. Now you've got to convert to polar and convert it back. It will save you time in the end. Form of complex numbers can help expedite and simplify calculations. We can also use the polar form to help us visualize sort of the motions that go along with some of these arithmetic operations. So let's take multiplication, for instance. All right. So when we multiplied z times w in the last example, z was 4 cis pi over 6, and w was 2 cis 2 pi over 3. So when we multiplied z times w, we multiplied the moduli and we added the angles. So let's break this down into a two-step process. All right. Step 1, let's multiply z by the modulus of w. So we'll take 4 cis pi over 6 times that modulus. That's going to get us to 8 cis pi over 6. And then the second step is now I'm going to add the argument. So I would be 8 cis pi over 6 plus 2 pi over 3, which gets us to 8 cis 5 pi over 6. So graphically or geometrically, multiplying by 2, right, is we're multiplying the radius by 2. So we're getting the new complex number is going to be twice as far out as the original one. So that's going to be now on a radius, instead of a radius of 4, it's on a radius of 8. And then we add 2 pi over 3 to the argument. We're rotating then counterclockwise an additional 2 pi over 3 radians. Right? So we can think of when the product here as multiplying, so a magnification of the radius, and then followed by a counterclockwise rotation. Similarly, when we divide, we can think of it the same way. So if I wanted to take z divided by w, first I can think of dividing by the modulus of w. So 4 cis pi over 6 divided by 2 to get to 2 cis pi over 6. And then the second is I'm subtracting. So that subtraction I can think of as a rotation clockwise. Right? So when you divide by 2, you're shrinking it. So now it's twice as close to the origin. And then subtracting rotates things clockwise by 2 pi over 3. And that lands you right down here on the negative y-axis, which would give you negative 2i. Okay? So that's another advantage to thinking about these in their polar forms, which with something which I think is one of the prettiest things you're going to see here in this curriculum. And that's the roots of a complex number. So what's a root of a complex number? All right. So just going back to the basic principles here. So a square root of 9 is any number that squares to 9. And we know that we get 2 of these, right? We get either plus 3 or negative 3. Okay? A cube root of 27 would be a real number that cubes to 27. And looks, we only get 1 of these. All right? But we know from college algebra that there's actually 2 more. So if I look at the function f of x equals x cubed minus 27, I know that 3 is one real solution. So if I go through my synthetic division here, I know that I can factor this as x minus 3 times x squared plus 3x plus 9. Now you might have remembered, I don't know what they have folks memorize anymore, but this is the difference of cubes, so that's another way to get to this. Or you can synthetically divide. Now, this polynomial down here that's left over, it doesn't have any real number solutions, but it does have two complex number solutions, two complex conjugates. I can go through and actually find these. If I look at the discriminant here, b squared minus 4ac, that would be 3 squared minus 4 times 9 times 1, so 36. So that gets me to what? Minus 27? And so x would be negative 3 plus or minus the square root of negative 27 all over 2. The negative comes out. It's going to give you the I. So negative 3 plus or minus. I've got a perfect square of 9 in there. So 3i square root of 3 all over 2. So these are two more cube roots of 27, but they're complex. They're non-real complex numbers. All right. So we could write this as minus 3 halves plus or minus 3 halves I square root of 3. You may or may not have remembered synthetic division, or you may or may not have remembered this. The point is we can actually get to all three of these cube roots using the polar form of a complex number. All right, so let's think of it this way. Let's think of, we want all the complex solutions to z cubed equals 27. And let's say z equals r cis theta. De Moivre's theorem says z cubed would be r cubed cis 3 theta. And I want this to equal 27 times, well, 27 is a real number, so that would be cis 0, right? What I'll do is I'll equate the equate the moduli here, and I'll solve for the angles. So if these are the arguments of the same complex number, they got to be off by a multiple of 2 pi k. So this gives theta would be 2 pi over 3k, where k could be 0, plus or minus 1, plus or minus 2. So r cubed equals 27, equating the moduli. Remember, these are distances, gives r equals 3. And then here are my thetas. Now, let's think what we get out of this. So r equals 3. That means we're on the circle of radius 3 here in the complex plane. When k is 0, I get 0. So here's one of them. That would be the point 3 cis 0, which is my real cube root 3. Then when k is 1, I'd be at 2 pi's over 3. That would be over here. 3 cis 2 pi over 3. Well, guess what that works out to be? 3 cosine 2 pi over 3 plus 3 sine, or 3i sine 2 pi over 3. That's going to be minus 3 halves plus, I'm sorry, that's 2 pi over 3 in there. It doesn't look good. Plus 3i square root 3 over 2. When k equals 2, I'm adding another 2 pi over 3. That'll get me down here to 4 pi over 3. And look what that gives me. 3 cosine 4 pi over 3 plus 3i sine 4 pi over 3. That gets me minus 3 halves minus 3i square root 3 over 2. And if I add another 2 pi over 3, I'm back to here. So notice, what did I get? I got 3 cube roots of 27. They're each 3 units away from the origin, and they're how far apart? 2 pi over 3 units apart. So 2 pi is all the way around. They're 3 equally spaced roots around the circle. In this case, it's a circle of radius 3. And by golly, aren't these the same solutions we got when we went through the quadratic formula? That you can get the roots of complex numbers this way, and the same sort of thing is going to happen. Okay? So this is basically, think of this as De Moivre's theorem in reverse. So De Moivre's theorem says if z is r cis theta, then z to the n is r to the n cis n theta. Right? You take the modulus to the nth power and you multiply the argument by n. So if you want an nth root, then you would do the opposite. Okay? So the nth root of z, instead of taking r to the nth power, you would take the n root of the modulus. And instead of multiplying theta by n, you'd divide theta by n. All right? But this is what would happen. Remember, any theta here, I could replace any theta plus, I could replace any theta with any angle coterminal to theta. So I'd have a plus a 2 pi k on there. So when I divide that by n, I'd get my theta over n, but I'd also get 2 pi over n times k. And then I would start running through my k's. Well, I'd have to run through from 0 to n minus 1 until I would get back, when k is n, the n's would cancel, I'd be back to 2 pi, it'd be coterminal to my initial one. So what this does is this gives us n distinct nth roots. So my example here with the 3, I had 3 distinct third roots, each of them 2 pi over 3 apart. So I had my first one here at the cube root of 27, 3, and I just added 2 pi over 3 until I got back to where I started. So I had 3 cube roots, 2 pi over 3 apart. So you get nth roots that are 2 pi over n apart. All right? So it's a nice, pretty little thing. So let's put this to some good use here. The first thing we need to do any of these things is we need to get the polar form of the complex number. So here it asks us for both square roots of this. So first off, we got to put this into polar form, and I believe this is one we did earlier. So this corresponds to the rectangular point 2 comma 2 root 3, which is over here. So in polar form, let's see, what would the modulus be? I'm sure we did this one. This is 4. So the modulus here is 4, and I can take theta to be 2 pi's over 3. So the polar form here is 4 cis 2 pi over 3. Now I want both square roots. So the square root, remember, that's the second root. So there should be 2 of them. So let's start. So I want the square roots. So to get the square roots, I'm going to get two of them. I'll call them z1 and z2. So I'm going to take the square root of the modulus. So 4, the square root of that is 2. Cis. And I'm going to cut the angle in half. So I'm going to divide 2 pi over 3 by 2. That's going to give me pi over 3. And I'll divide 2 pi divided by 2 pi. So I'm going to get two roots that are pi units apart. The first one will be pi over 3, and the second one will be pi over 3 plus pi. So I can work this out. 2 cis pi over 3. Cosine of pi over 3 is a half times 2 is 1. Plus sine of pi over 3 is root 3 over 2 times 2 is root 3. So 1 plus I root 3. Now cis of pi over 3 plus pi, that's going to put me in the third quadrant. That's before pi over 3. So here, cosine of 4 pi over 3 is negative 1/2. So that's a negative 1. Sine of 4 pi over 3 is negative root 3 over 2, negative I root 3. So these would be the two square roots of negative 2 plus 2i over 3. Now let's just check one of them, just to show you that this is actually working here. Let's just take one of these and square it. So how could you check it to make sure that this wizardry is working here? Well, let's take 1 plus I square root of 3 squared. When in doubt, write it out. So 1 times 1 is 1, plus 1i square root of 3, 2i square root of 3, plus I squared square root 3 squared. 1 plus 2i square root of 3. I squared is negative 1. Root 3 squared is negative 3. And by golly, look what we get. Negative 2 plus 2i square root of 3. So this thing squared is going to give you that. Boom. And now if I look at the second one here, the second one is just the opposite of the first one. Right? So when I square this, I'm going to get back to that as well. All right? So it works. But whoever thought you'd be trying to take the square root of something like this, right? All right. Let's look at the next one. I want the 4 fourth roots of negative 16. So let's put this in polar form. We didn't do this one already. But the polar form of this one is not hard to get. Negative 16 would be over here in the complex plane. It's 16 units away from the origin, so I know the modulus. And the angle would be pi. So I can write z as 16 cis pi. I want the fourth roots. I know there's going to be 4 of them. The modulus of each of these is going to be the fourth root of 16. So fourth root of 16, which is 2. Cis, what are the angles going to be? Well, since I'm taking the fourth roots, I'm going to take pi and divide it by 4. Or any multiple of 2 pi divided by 4. So I'm going to start with pi over 4 plus 0. Then I'll go to pi over 4 plus what? Well, 2 pi's over 4. And then pi over 4 plus 4 pi's over 4. And then pi over 4 plus 6 pi's over 4. Okay, so I divide by, I take the fourth root of the modulus, I divide the angle by 4, and then I add 2 pi over 4s as I go down. So plus 2 pi over 4, plus another 2 pi over 4, plus another 2 pi over 4. And now we're going to simplify all this. So 2 cis pi over 4, 2 cosine of pi over 4, plus 2I sine pi over 4. Sine and cosine of pi over 4 is root 2 over 2. So I multiply by 2, I get root 2. So I get root 2 plus I square root of 2. C2 would be 2 cis 3 pi's over 4, which would be pretty much the same thing, except now I'm in quadrant 2, so the cosine would be negative. Adding 4 pi's over 4 would get me to 5 pi's over 4. Now I'm in quadrant 3. Both of these are negative. Now I'm at 7 pi over 4. I'm in quadrant 4. So that means the cosine is positive, but the sine is negative. And there are your fourth roots of negative 16. You take any one of these to the fourth power, you're going to get negative 16. Okay. So this is actually a very pretty thing. We've got this kind of sketched out here. So you notice each of these is now 2 units away. So that's the new modulus, is the fourth root of 16. All right. And they are, what are they? Let's see, they're 2 pi over 4. Pi over 2 apart. Okay. So these are all at 90 degrees. So all of these here are at 90 degrees to each other. All right. Which is pretty cool. The last example I want to talk about here is finding the sixth roots of z equals 1. Oops. Now, when you go to the roots of 1, oops, are also called the roots of unity. And they have a lot of nice properties that we'll sort of just talk a little bit about. But, you know, be great for a project. So here's the thing about z equals 1. If you think of z equals 1, here it is in the complex plane. It's 1 unit over from the origin with an angle of 0. So z equals 1, that's 1 cis 0. So it's just cis 0. And so if I want to find the roots of this, right, I would take the sixth root of 1, which is 1, and I would just be taking 0 divided by 6 and adding 2 pi over 6. So the sixth root of 1 is 1. 0 over 6 is 0. 2 pi over 6k is pi over 3k. All right. So what you end up getting, z1 is, well, cis 0. You just get 1 back, which hopefully makes sense. Z2 would be cis. Now I'm going to add pi over 3, cis pi over 3. So that's going to be 1/2 plus I square root 3 over 2. Z3, you'd add another pi over 3. So you'd be at 2 pi over 3, which would be minus 1/2 plus I square root 3 over 2. Z4 would be cis 3 pi over 3, because you're adding another pi over 3. That's at pi. Cis pi be cosine of pi plus I sine pi. Now you're at negative 1. Z5 would be cis 5 pi over 3. Let's see. No, excuse me. 4 pi over 3. I skipped 1. 4 pi over 3, which would be minus 1/2 minus I squared 3 over 2. And the last one, z6, would be cis 5 pi over 3, which would be 1/2 minus I square root 3 over 2. So you start at 0, and then you add pi over 3's. You're just working your way around the unit circle because we're on a circle of radius 1. All right, so we can plot these out. I'm going to use Desmos to help us because Desmos has a nice polar graph for us. Oh, almost thought it wouldn't show up. So let's just blast over to here. And we'd be on a circle of radius 1. We'd be on the unit circle. And so here are the sixth roots. So we were at cis 0, and then pi over 3, and then 2 pi over 3, and then pi, and then 4 pi over 3, and then 5 pi over 3. So they're nice and equally spaced around the circle, pi over 3 apart, as all nth roots are. But here's what's neat about the nth roots of unity. Okay? Because each of these have a modulus of 1. All right? So what happens if I multiply two of these things together? So what if I happen to take cis of alpha times cis of beta? All you're doing is adding those angles. Cis of alpha plus beta. Okay? Well, think about it. These are all equally spaced pi over 3 apart. So let's say I take this one. Let's say I take cis of pi over 3 and I multiply it by, I don't know, 5 pi over 3. All I'm doing is adding these. This would get me to 2 pi, which would be really right back to here. So when I multiply any two of these together, I'm going to get another one in the list. Okay? And this is what is called this forms what's called a mathematical group. In other words, if you multiply any two of these roots of unity together, you're going to get another root, sixth root of unity, which is pretty cool because you're just doing that rotation as you go around the circle. So roots of unity are pretty cool. They're a classic example later on in abstract mathematics. So it's just something fun to point out. All right, so that'll do it for our brief excursion back into the complex number.